So the first part we learned in chapter 5 is about isomerism, and we learned the types of isomerism and what usually those isomerism do have in order for us to label them, whether structural isomerism or stereoisomerism. We will learn in this part much more details into stereoisomerism, the terms that we heard, enantiomers, diastereomers, chiral, achiral, meso, all that will appear in this part again. So this picture should always remind you that chirality between two compounds should always fulfill the requirement of having those two compounds mirror image of each other, non-superimposable. So that's why we always say our hands are chiral, Versus this one, you could see clearly that if you would have a chair sitting in front of a mirror, that these two compounds are basically mirror image of each other, but they are superimposable. So the fact that they are superimposable, automatically, you cannot label them enantiomers. You will have to label them basically identical, which means achiral. So every single time you hear the word enantiomers, you should always define it as compounds that have same connectivity, same chemical formula, but there are different arrangement in space, meaning these compounds would be mirror image of each other. Like in this example, you could see here that this compound is a mirror image of the second, and not just that, non-superimposable. So if I would take this molecule and put it on the top of the other, they are not the same. So you could see here the 3D formula of the ball and stick formula above. You can see it clearly here that the Br pointing towards you, hydrogen pointing away, the methyl and the ethyl, they are on the plane. In this formula, you could see here that the Br in the mirror, you could see it mirror image, hydrogen mirror image, ethyl is also a mirror image. So these two compounds are not just mirror image of each other, they are also non-superimposable. That's what makes them enantiomers. Every single time we hear the term chiral atom, we should think of an atom that has 4 different atoms or groups of atoms. And carbon is an example of that. That's not the only example, but it's a common example that you will see it in organic compounds. The term asymmetric carbon means that you have no symmetry around it in terms of groups attached to it. So when you have the asymmetry around that carbon, we will label that carbon basically an asymmetric carbon, means it is eligible to be a chiral center. And there is a difference between chiral center and a stereocenter. Chiral center is when you have an atom with 4 different groups of atoms or atoms. When you have a stereocenter, it means that you have a side of the molecule. If you would switch 2 atoms in it, you would generate a second isomer. And the stereocenter, we usually see it in cis and trans alkenes or cyclic alkenes. But when we hear the word chiral center, we usually see it in enantiomers and diastereomers or meso compounds if they happen to be the ones that we are looking at. And that's basically the definition of chiral center versus stereocenter. So keep that in mind, that there is a difference between the two. So those compounds that are geometric isomers, whether they are cis and trans alkene or cis and trans cycloalkanes, they are diastereomers and they have stereocenters. But those compounds that are non-cis and trans alkenes, non-cis and trans cyclic alkanes, but they do have chiral centers, they can basically be enantiomers or diastereomers because of the existence of the asymmetric carbon in them. So here are some examples. You could see here the one on the left. It's a carbon with 4 different groups of atoms. So you can see here a hydrogen, Br, methyl, ethyl. So that's a stereo center, and it's a chiral center. You can see here that you have also another example. So you have a nitrogen with 4 different groups of atoms that makes this a chiral center and a stereocenter. And you can see here that you have an alkene that's a cis. It's not a chiral center, but it is a stereocenter because the moment I take this methyl and put it right there, I will generate the other stereoisomer, which is the trans. So that's clearly indicates how I would label a chiral center versus a stereocenter. All chiral centers are stereocenters, but not all stereocenters are chiral centers. Those stereocenters that exist in alkenes, they are not chiral centers. Achiral compounds, those are the ones that usually have no chiral center, or they have plane of symmetry. So you could see clearly here that you have a carbon with two similar groups attached to it, that would make the compound right away an achiral compound. So you could see here also that achiral term is used when you have a compound that has a plane of symmetry. Plane of symmetry means divides the molecule into two halves that are exactly the same. And that's why I would be also able to use the term achiral if I see a molecule that has a plane of symmetry. So you see that even though it's a cis cyclic alkanes, but because of the plane of symmetry, automatically makes the compound an achiral compound. What if I have a trans? The trans cyclic alkane is not gonna be a compound that's achiral because of the fact that the plane of symmetry doesn't exist. So if I see this molecule and I see the one on the right, what do I have here? I have a chloro down, chloro up, chloro down, chloro up. So these two are mirror image of each other and non-superimposable. If I would put a mirror in between, this will see itself in the mirror. And if I take this molecule and put it on top of the other, they are non-superimposable. Therefore, these two compounds are enantiomers. So same connectivity, mirror image of each other, non-superimposable. And this is where it's important to distinguish the two different spatial arrangements in molecules. What is that supposed to mean? I have this compound and this. If I look at the two, I would be looking at them and say, oh, alanine. But is that enough? If I draw alanine, somebody might draw the hydrogen pointing away, and the amino group pointing towards, or I could be switching them around, and I will be confused. All right, well, it doesn't seem that the two molecules have the same arrangement in space. And therefore, more specification when it comes to naming a compound that has to deal with different arrangement space is required. And that's where we see the R and S configuration. So the 2-amino-propanoic acid can be drawn in both ways, but these two both ways are not the same. One of them is a natural alanine, and the other one is a synthetic alanine. It's an unnatural one. So we should be actually having a system in place to distinguish between those two compounds. And that's what we have here. The Kahn-Ingold Prelog in convention. Kahn-Ingold Prelog convention is what we use to determine R and S of those chiral centers. And again, we don't use R and S for an alkene. We don't use R and S for compounds that are achiral. We use R and S for compounds that have a chiral center in them. And the two possible arrangements usually are referred to as configuration. So I could have an R configuration or I could have an S configuration. And let me highlight one thing here. The polarimeter that we talked about earlier has nothing to do with R and S. I could have a compound A, that's an R configuration, and I see it in the polarimeter rotates the light to the right, meaning dextral. I could have another compound that's an S configuration, and I put it in the polarimeter and I see it rotating the light to the right as well. So I need to make a distinction between the polarimeter checking optical activity, how the plane polarized light being rotated, and between the Kahn-Ingold Prelog convention assigning R and S. Assigning R and S is for the purpose of being able to IUPAC name the structure. IUPAC naming pushes me to recognize or to acknowledge the existence of the chiral centers in the compound. And that's where the importance of the Kahn-Ingold Prelog convention for those compounds that have a chiral center. What is this convention? it depends on several steps. One, assigning priority. Didn't we just say chiral center is an atom with 4 different atoms or groups of atoms? All right. Priority need to be defined. I need to look at those 4 groups and label them 1, 2, 3, and 4. How am I going to be labeling them based on? Number 1 will be the highest in priority. Number 4 will be the lowest in priority. Number 1, highest in priority means the biggest in terms of atomic number. So whether I look at atomic number or atomic mass, it's the same thing. So look at this. Iodo, bigger than bromo, bigger than chloro, bigger than all the rest of the atoms. So you can see here, they are arranged in terms of decreasing atomic number. So that's the first thing I need to keep in mind, that I recognize where the chiral center is. That means I have to have 4 different atoms or groups of atoms. And then I label them based on a priority in terms of atomic number. So here's an example. You could see that a carbon attached to 4 different atoms. So you have a carbon, hydrogen, nitrogen, and a fluoro. The very first thing I need to look at, the atoms directly attached to the chiral center. I have a carbon, atomic number or atomic mass of 12. I have a hydrogen, atomic mass of 1, nitrogen 14, fluoro 19. So obviously fluoro would be the biggest. So the highest in priority would be number 1 for the fluoro. Next would be the nitrogen. Third will be the methyl. Fourth will be the hydrogen. Somebody might say, okay, do we add up the hydrogens? No, you do not. You look at the atoms directly attached to the chiral center. And that's what you need to look at in terms of atomic number, just that atom. What if I have 2 similar atoms? Then you need to look at the adjacent atom that's attached to it. Now let's look at the examples. So if I have here a bunch of groups, and I look at here, I have a carbon attached to a Br. So assume you have 4 different groups of atoms, and you are debating between this one and this one. Okay, this one has a bromo, even though these 2 are carbons, but this one has a bromo attached to it. This one has chloro attached to it. The moment you find a group has an atom with heavier atomic mass, automatically it gets a priority over the other. So here's an example. You have a CH2Br, heavier, considered heavier based on Cohn-Ingold pre-log convention than a CHCl2. Even though if you would add up the atomic mass, you may end up, okay, well, you may end up having, bigger atomic mass if I have 3 chloro. Well, that's not how we look at it. We look at the existence of 1 atom at least to be the biggest in atomic size, or the bigger in atomic size. Atomic mass. So whether you look at atomic number or atomic mass is the same thing. So here you could see an example where you have 2 chloro versus 3 methyl. Aromatically, this will be higher in priority. I have 3 carbons and 2 carbons and a hydrogen. So obviously the ones that has 3 carbons versus 2 carbons and a hydrogen will be heavier. I have 2 carbons attached versus only 1 attached. So the directly attached atom to the CH2, you have 1 carbon and 2 hydrogens versus 2 carbons and 1 hydrogen. So that's why this will be ranked higher in priority. So again, ranking in terms of priority will always depend on atomic number or atomic mass. What if I have double bonds? So I look at the 4 different groups of atoms, and I see there is a difference in multiple bonds exist in those groups. Well, how do we view that? The double bond, you need to view it as multiple atoms attached, meaning this carbon is double bonded to the other. That means this carbon has another carbon, and the one on the right has another carbon. So this is how you need to view them. I'm not saying that these 2 carbons have 2 carbons attached to them, but you need to view them in terms of ranking their priority when it comes to Cohn-Ingold pre-log convention. That's how the rule is when it comes to double bonds. Same thing here. When I have a C double bond M, I will rank this in a way that considering the carbon is attached to a nitrogen and the nitrogen is attached to another carbon. So that's how I need to view it. Same thing here, C triple bond C. How do I view that? This carbon, besides this carbon that's already attached to it, I will need to assume that there are two carbons attached to it. And this carbon on the right, besides the one that's attached to it, I would need to assume also two other carbons attached to it. And that's how I would view that group. And that's how I would see it higher in priority than another. Same thing here. I have a carboxylic acid. The carbonyl would be viewed as C single bond O, O single bond C. That's what you see here. So let's look at examples and see how we usually, once we rank those groups in terms of priority, 1, 2, 3, 4. Now what? We need to keep in mind that the ideal situation for a chiral center is to have the fourth group pointing away from us. So meaning dash bond. That fourth group, when it's dashed away from us, if the rotation, if the direction of the priority going from 1 to 2 to 3 to 4 is clockwise, the chiral center is labeled R configuration. But if the fourth group is pointing away and the rotation going from 1 to 2 to 3 counterclockwise, then the configuration would be labeled S. So two main important configurations that you need to keep in mind when it comes to Canning-Gall-Clorod convention, R and S. R is when you have a priority 1, 2, 3, 4 clockwise, fourth group pointing away. S is when you have 1, 2, 3, 4 counterclockwise, fourth group is pointing away from us. I don't want to complicate it now, but let me just mention the other two scenarios, and we will see examples later. What if I have clockwise 1, 2, 3, 4, but my fourth group is not away, it's towards me? That means it's not R anymore, it's an S, because the R has to have the clockwise where the fourth group is pointing away. So if that fourth group is pointing towards you and it's a clockwise, that means it's an S configuration, and that will be the second possibility for an S configuration. What if I have an S rotation? It looks like it's a counterclockwise, 1, 2, 3, 4, but my fourth group is not away, where I would be labeling an S. If it's not pointing away, it's pointing towards you, and you see it's a counterclockwise, that means it's an R configuration. So there are two possibilities for R configuration and two possibilities for S configuration. The two possibilities for R configuration is when you have the priority of 1, 2, 3, 4 clockwise, fourth group away. And the second possibility is when you have 1, 2, 3, 4 counterclockwise, fourth group pointing towards you. S configuration, two possibilities. The first is when you have 1, 2, 3, 4 counterclockwise, fourth group pointing away. And the second possibility for S configuration is when you have 1, 2, 3, 4 clockwise, fourth group towards you. Just keep that in mind. Write that down on a piece of paper and remind yourself of those four different scenarios when you deal with a 3D formula. Here's the first example. Alanine. I want to apply R and S here to make sure that we recognize what kind of configuration we have. All right. First step, label priorities. I have nitrogen. First of all, figure out where the chiral center is. So the chiral center should have 4 different atoms or groups of atoms, and that would be the one in the center. I have a hydrogen, nitrogen, carbon, and another carbon. Okay. So in terms of atomic number, which of those will have the highest? Well, obviously the nitrogen. So nitrogen will be number 1. Next, this carbon or is this carbon? Well, both are the same. That means I have to look at what's attached to them now. This one has 3 hydrogens. This one has an oxygen and another. So definitely this would be heavier. So this would be number 2. Next would be number 3. Next would be number 4, which is the hydrogen. Usually hydrogen has the lowest priority because atomic number is 1. What do I have now? I have 1, 2, 3, 4. Okay. How do I set the rotation? I need to set the rotation going from 1 to 2, crossing 4, but not crossing 3. Once again, I need to set the rotation going from 1 to 2, crossing 4, not crossing 3. Why? Because if I do cross 3 going from 1 to 2, that's like labeling 3 as number 2. And that's the mistake to commit if you are dealing with a Carroll center trying to define its configuration. Kahn-Ingold pre-law convention forces us to set the rotation going from 1 to 2, crossing 4, not crossing 3. So what do I have here? I have 1 to 2, crossing 4. So what is that? That's a counterclockwise, fourth group pointing away. What kind of configuration I'm dealing with? That's an S configuration. That's an S configuration. How would I switch this to an R configuration? I would be switching H with an NH2. If I would be switching H with NH2, I will be able to get the other stereoisomer, which is the other configuration. So once again, 1 to 2 to 3, crossing 4. So that's counterclockwise, fourth group pointing away. So that's an S configuration. Let's look at another example. What do I have here? I have a Carroll center, oxygen, carbon, and another carbon, and a hydrogen. What would be number 1 in terms of Kahn-Ingold pre-law convention priorities? Oxygen, number 1. Next, this group or this group? Well, I have two. I have a carbon attached to another. I have a carbon attached to another. Okay, but this carbon has 2 hydrogens and a carbon. This carbon has 2 hydrogens and this carbon has 2 hydrogens and a carbon versus 3 hydrogens here. So definitely the propyl will be heavier than the ethyl. Therefore, this will be number 2. This will be number 3. Hydrogen will be number 4. Okay, let's do the rotation now. What do I have? I have 1, 2, 3. So what is that? That's a counterclockwise, but my fourth group is pointing towards me. We just said the second possibility for an R group, for an R configuration, is when the rotation is counterclockwise and fourth group is towards me, because that's the opposite of the ideal situation for an S. S configuration is when you have the counterclockwise fourth group away from you. But what if it's counterclockwise fourth group towards you, like this example? That would be an R configuration. That's the second possibility for an R configuration. Here's another example. You could see here that I have carbon, 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 but this carbon is a methyl. This carbon is a butyl, but this carbon has a double bond in it. So automatically, the C double bond C will right away have a higher priority than a C single bond C. So that's why this would be number 1. This would be number 2. Methyl would be number 3, and the hydrogen would be number 4. All right. What do I have here? I have 1, 2. So it's a counterclockwise, and my fourth group is away, right away. That's an S configuration. So let me remind you of those 4 scenarios once again when I'm dealing with a 3D before we see other examples. The first scenario for an R configuration, groups being assigned 1, 2, 3, 4 with a clockwise and fourth group pointing away from me. The second scenario for an R, groups assigned 1, 2, 3, 4 counterclockwise, but the fourth group is pointing towards me. The third scenario, which is the first scenario of an S configuration, groups assigned 1, 2, 3, 4 counterclockwise, fourth group pointing away. The second scenario of an S configuration would be when you have 1, 2, 3, 4 groups assigned clockwise, but the fourth group is towards me. These are the possibilities for R and S when you deal with a 3D configuration. Later on, we're going to look at chair conformations. We're going to look at Fisher projections. These are going to follow different set of rules that we will have to look at than the ones that we are looking at now for assigning R and S in a 3D formula. Keep that in mind. So here's another example. We could see here that the bromo is number 1. This carbon is higher in priority than the other. So somebody would say, wait a minute, this carbon has a bromo on it. Well, when we assign priority, we need to look at the atoms directly attached to the chiral center first. Bromo is heavier than this carbon and the other carbon. So right away, this would be number 1. Now, this carbon or that carbon, this carbon has 3 hydrogens, this carbon has 2 hydrogens and a carbon. So right away, this would be number 2. And this methyl would be number 3. Now, what do we have? And this obviously hydrogen will be number 4. What do we have here? We have 1, 2, 3. So that's a clockwise with 4th group pointing away. So that's an R configuration. Look at the one on the right. What do we have? We have 1, 2, 3. So it's a counterclockwise, 4th group pointing away. So that would be the S configuration. What's the relationship between these two compounds? R and S, same connectivity, same chemical formula, mirror image of each other, non-superimposable. These are enantiomers. So the moment you see that you have pair of compounds, one of them is an R and one of them is an S, you don't need to think twice. That makes the two structures enantiomers right away because they are mirror image of each other, non-superimposable. Let's look at this compound. What do we have? We have a chiral center right there with 4 different groups of atoms. So we have a hydrogen, we have an isopropene, and you have basically 2 CH2s. But these 2 CH2s are not the same. You have a CH2 attached to a carbonyl, you have a CH2 attached to an alkene. So that makes carbon number 2 and carbon number 3 are not the same. Okay, which of those is going to be the highest in priority? Well, this carbon is an alkene already versus these 2 carbons are sp3s. So right away, the carbon with an sp2, the alkene, is going to be the highest in priority. So this would be number 1. Next, which of the 2 would be next? Well, the one that's attached to a carbonyl is going to be heavier than the carbon that's attached to an alkene. So these 2 sides are double bonds, but this one has an oxygen at the end, this one has a carbon at the end. So that's why this will be number 2, this would be number 3. Hydrogen will be number 4. So what's the rotation here? I have 1, 2, so you need to cross 4, not 3. So this is counterclockwise, 4th group away, so that's an S configuration. S configuration. How can I make this an R configuration? It's a very simple process. You switch the dash with the wedge. So instead of having the hydrogen being dash, make it a wedge. And instead of making the alkene unit, the substituent, being wedge, make it a dash, which means the opposite of these 2 bonds. That will generate the R configuration. Put that on a piece of paper and assign the priority, then visualize the configuration rotation yourself. Every single time we deal with the enantiomers, we need to keep in mind that they have similar physical properties, melting point, boiling point, solubility. They may have different properties such as tasting or sensing in that direction if they have that activity, but they're always going to be different in terms of plane polarized light activity. They will not, those enantiomers will not rotate the plane polarized light in the same direction. They will always rotate the plane polarized light opposite to each other. So that's what they are different in all the time. So they are always similar in terms of physical properties and even chemical properties, but they are different when it comes to rotating plane polarized light. That's different from diastereomers. Diastereomers, they can be different in terms of physical properties or chemical properties. So that's the distinction between enantiomers and diastereomers. Enantiomers, they have same physical properties, same chemical properties, but different rotation of plane polarized light. Diastereomers, they have different chemical properties and physical properties. The plane polarized light, as I mentioned earlier, it's basically a machine that we use polarimeter, and this polarimeter is going to have a sample injection spot. We inject the sample in it, and we wait for the optical activity to be reported. The amount of rotation will always be presented in a degree angle of that plane polarized light, how much it got rotated. Every single time we deal with enantiomers, we have to always observe, in order for them to be enantiomers, they have to rotate the plane polarized light in the same amount, but opposite direction. So one would be like minus 12 degree, the other one would be plus 12 degree. That's just an example. So the rotation of the plane polarized light has nothing to do with R and S. I know you just heard the term clockwise and counterclockwise when we assign configuration of R and S, but that's totally different from the clockwise and counterclockwise being utilized in the polarimeter. Polarimeter, it's for the purpose of identifying optical activity. R and S, Canning-Gold-Trilog convention, is for the purpose of naming the compound properly. That's the difference between the two. Every single time the plane polarized light being rotated clockwise, it will be dextro or positive. Every single time the plane polarized light is rotated counterclockwise, would be levo or L and minus. Okay, and as I mentioned, not related to R and S. That's important. So grab a drug from the cabinet and you will see an active ingredient. You may see in front of it a minus or plus. What is that supposed to mean? It means this, the active ingredient been put in a polarimeter, and the polarimeter showed the plane polarized light being rotated to the left if it's minus, rotated to the right if it's positive. Specific rotation. Those samples that we put in a polarimeter, what do we expect to see at the end? We expect to see what we call specific rotation. The specific rotation, we may need to calculate it if the machine doesn't calculate it for us. So some machines will probably give us the observed rotation, which is alpha. Some machines will give us the entire thing, which is the specific rotation. So the specific rotation is a physical property of a compound, usually reported in literature. So those compounds that have chiral centers, they have melting point, they have boiling point, they have solubility reports, and they're also going to have what we call specific rotation. How do we calculate the specific rotation? Specific rotation is calculated as the following. The observed rotation by the machine divided by concentration in gram per ml, concentration of the sample, times length of sample cell, which usually has to be in decimeter. So you have the observed rotation by the machine, and you have the concentration of the sample, which you should already know before you injected the sample, and the length of the cell that you placed the sample in before placing it inside the polarimeter. These are the three criteria that we need: the observed rotation, the concentration of the sample in gram per ml, and the length of the sample cell in decimeter to calculate specific rotation. Here's an example. When one of the enantiomers of 2-butanol is placed in a polarimeter, the observed rotation is 4.05 degree. That's alpha. Counterclockwise, meaning it's negative. Okay. The solution was made by diluting 6 grams of 2-butanol to a total of 40 ml. So I know I have a concentration of 6 grams over 40 ml. 6 grams over 40 ml. And that's basically 0.15. Okay, gram per ml. And the solution was placed into a 200 millimeter polarimeter. Millimeter. I can't just plug this length in the equation. I have to have it in a decimeter. Knowing that there are 10 decimeter in a meter, do the math yourself. You will find that the length of the sample cell is 2 decimeter. All right. Determine the specific rotation. I have the equation already in my mind. I'm not going to look for it on an exam handout because it's not going to be given to me there. Therefore, I have to keep in mind this equation. Specific rotation always equal observed rotation over or divided by concentrations times length. The observed rotation is 4.05 divided by the concentration, which is 6 over 40, that's 0.15, times the length of the cell, which is 200 millimeter converted to decimeter, that will be 2 decimeter. Do the math, you will find it to be minus 13.5. Where did the minus come from? He just said it right there. counterclockwise in a polarimeter refers to rotating the polarized light to the left, LIVO minus. And that's why the final value for the specific rotation measured at room temp, and that's what the 25 means, usually is the value degree angle. So the degree means how much the plane polarized light been rotated. So that's a very important physical property that we need to make sure that we are able to calculate if the machine doesn't give it to us, meaning specific rotation need to be calculated from the alpha observed rotation. Here's an example of a biological activity that's usually released or not released depending on the stereochemistry of the compound. So I see here that I have the R minus epinephrine, which is the natural one, and I have the S plus epinephrine, which is the unnatural one. If I would inject this into the cell, I see the enzyme active site gonna recognize these groups on the compound and will place them in the right buckets, and those automatically will click the complex to release the activity. Versus if I would have the other configuration, you can see here clearly that this is an R, this is the S. If I place this into the cell, you will find that the two part of the compound here, as you can see, the OH and the amino site, this will not fit into the bucket, and therefore the whole site will not be activated. And that's where you need to keep in mind all these drug compounds or those enzymes, how they behave when we inject them in our bodies. The way how the drug works, it usually finds the active site, and not just that, it has to fit in it, meaning the groups that are in the drug structure, they have to basically find the match in the other side, which is the binding site, the bucket. And once it matches, that's where basically the biological activity is expected to be released. And that's very important aspect that we need to keep in mind when we think of stereochemistry, not just drawing R and S, and not just figuring out whether it rotates the light to the right or to the left. We need to think of the bigger picture, the application of this into basically the drug industry or biology field as well. Here's the term again that we've seen earlier, racemic mixture. What is that supposed to mean? It means that you have two compounds, have the same connectivity, same chemical formula, but different spatial arrangement. So one would be an S, one would be an R. You would expect one would rotate the plane polarized light opposite to the other. So you can see clearly when you have the mix together, that mix put into a polarimeter will cancel the optical activity. Therefore, you will end up having a racemic mixture with optically inactive compound. So that's very important to keep in mind when you have equal quantities of the two. So what if I don't have equal quantity? What if I have a mixture of the S plus butanol and the R minus butanol, but these two are not 50-50? They are not racemic mixture. Then I'm dealing with something else that is optical pure compound. What is that supposed to mean? Let's talk about that. But once we look at what else we will notice if we deal with a compound that can go through, this is a compound, can go through a reaction, like this carbonyl reacting with hydrogen. This hydrogen can be delivered from the top or can be delivered from the bottom. That means I could end up always making a racemic mixture if the reaction allows for such. Because here is a reaction, I cannot control the hydrogen to be delivered from the top or to be delivered from the bottom. The fact that I'm dealing with a trigonal planar bond, trigonal planar carbon, the hydrogen, when it comes to be delivered, it could deliver from the top or the bottom. Therefore, I could end up having an R configuration or an S configuration. And therefore, I will always expect a racemic mixture of those reaction that start with an optically inactive compound. So this is an optically inactive, end up having two structures that are racemic mixtures. And this racemic mixture, once again, the reason why we use the term racemic mixture because it's a 50-50 in terms of percent yield. 50-50 in terms of percent yield. The moment you see that a mixture of enantiomers have not 50-50, one of them is more than the other, that means I have to calculate something called optical purity. What is optical purity? Or sometimes called enantiomeric excess. So OP or EE. Is there a difference between the two? No, both are exactly the same. One enantiomer is present in greater amounts. That means I'm not dealing with a racemic mixture anymore. I'm dealing with a mixture of two enantiomers. One of them exists in higher yield than the other. How do I calculate that? I calculate it by the following equation. Observed rotation. So I take that sample of the mixture and I put it in a polarimeter. It's going to give me an observed rotation. That observed rotation, I need to divide it by the rotation of the pure enantiomer that matches the sign of the observed rotation. Meaning, if the observed rotation was negative, that means I need to divide it by the negative value of that pure enantiomer. If the observed rotation was positive, I need to divide it by the rotation of the pure enantiomer that's in the positive value, times 100% to get the percent of the optical purity. So whether I say optical purity or enantiomeric excess is the same thing. This equation is important for you to remember. It will not be given to you in the exam handout. So the specific rotation equation and the optical purity or enantiomeric excess calculations, you need to keep that in mind. How do I calculate this? Well, let's take an example. Here is one. Calculate percent composition. So you have a sample and you're asked to find out how much percentage of R versus S or D versus L. Okay. The question says specific rotation of S2-iodobutane is plus 15.9. That's a specific rotation of 1. So you would expect right away that R would be the opposite, obviously, which is the minus 15.9. Okay. Determine the percent composition of a mixture of R and S, 2-iodobutane, if the specific rotation of the mixture is minus 3.18. How do I know it's not a racemic? Because I have a value for the plane polarized light being rotated with the mix. If it would have been a racemic mixture, I should be getting a specific rotation of 0. But the fact is giving me minus 3.18. What does this value mean? That means I have more of R than S. More of R, which is the minus 15.91, the opposite to this, than S. But how much more of R do I have? And this is where I need to do the math. Observed rotation, which is the minus 3.18, divided by what? Rotation of the pure enantiomer that matches the sign of the observed rotation, which was what? The 15.9. So usually it's an absolute value. The percentage wouldn't be negative. So that's why you would need to divide the minus with the minus. So the minus 3.18 divided by the minus 15.9 times 100, you will get 20% optical purity. What is that supposed to mean? When I say 20% more of R than S, how do I translate that? What it means that I have 20% of R more than S, or L more than D, plus the 80% remaining, they are divided 50-50. So I have 40 D and I have 40 L, 40 R and 40 S. So I know already that R exists in 20% more than S. In addition to that, I have 40 and 40 divided with the remaining 80. So every single time I look at a value that's 20% optical purity, how do I read it? I read it as the following. 20 of the enantiomer that exists in excess. And how do I know it exists? Which one exists in excess? I look at the sign. The sign here indicates it's the R. It's not the S. Why? Because the S is positive rotation. So now I have 20% R. What else? I have 80% remaining. They are divided 40-40. So what that gives me of R? I have 60% total versus 40% of S. What if I have, and as an example, what if I have optical purity or enantiomeric excess calculated and giving me 80% of R? What is that supposed to mean? 80% means I have 80 R and the 20% remaining divided 50-50. So what does that end up having for the composition? I have 90% R, 10% S. Let's take another example. I have 60% excess of S. How do I read that? How do I translate that to percent composition? What it means, I have 60% S and 40% remaining that are divided 50-50. That means I have total of 80% S, 20% R. You could rewind the tape and look at those examples one more time. Do these questions yourself. Make sure you are able to reproduce them. And that's the part I want to talk about in this chapter. Next part, we will be discussing how to assign configuration of R and S when it comes to chair conformation, Fisher projection, and furthermore, examples that we're going to be also looking at to strengthen our skills to assign R and S.